Hello, I am Anthony Atkinson.
And I am Marco Riani. We are here to give you a brief illustration of the context of our new book.
Marco and I have been working together on this material for over 30 years, so this is going to be a very brief approach to a large amount of material. So, Chapter 1, we start with introductions to some of the concept of robust regression, concepts of breakdown point, and the efficiency of estimation, and the ideas of rates of convergence as the sample size gets larger. We look at two data sets. One is a set of income data from the American Census Bureau, and the other are income data from a municipality in the north of Italy. And the statistical point is that the data need to be transformed. Chapter 2 is the most theoretical chapter of the book. We give an introduction to the mathematics of robust statistics, such ideas, concepts as the influence function, maximum bias, the sensitivity curve, and gross error sensitivity. One of the sets of robust methods that we are interested in and that we analyze and work with a great deal are the derivatives of extensions, perhaps, of M estimation, that's maximum likelihood estimation, in which the extreme observations are down-weighted using various row functions and their derivatives. These are usually described at the moment for given values of the breakdown point or the efficiency. These, having specified these values, the form of the particular member of the row family is determined. We look at theoretical comparisons of row functions, and then we look at empirical comparisons using simulated data.
What are the conclusions from the comparisons?
The theoretical comparisons come from asymptotic comparisons of the different row functions. For given breakdown point or efficiency, the conclusion is that there was little difference between their properties. However, the empirical comparisons, in which the breakdown point or the efficiencies vary the kind of row function, is again not important. However, the behavior of the row function for the particular value of breakdown point or efficiency will be very different as these parameters vary.
In Chapter 3, we go to multiple regression.
The results of the previous chapter were to do with estimations of the location in a sample. We now extend these methods to robust estimation in multiple regression. We introduce several forms of robust regression, the SMM, tau, LMS, and LTS estimators. The first three of these are forms of M estimation. The last two are variants on least squares estimation. In all of this, again, the breakdown points or efficiency of the first three sets of estimators are prefixed. You can think of these as just providing a snapshot of the data. If I believe that there are 10% of outliers in the data, then that will fix the BDP that I use, but I have no idea what happens if I've actually got the statement about the belief about the BDP being wrong.
In Chapter 4, we introduce the monitoring approach in multiple regression.
So the idea is that we look at what you could think of as a movie or film of the data. We look at robust analyses for a range of values of BDP or efficiency, or for methods that are based on subsets for a range of subset sizes of the data.
The result indeed is a movie of the data, a film, rather than a snapshot of the data as in the previous case where the breakdown point or efficiency was prefixed.
In the book we analyze many sets of data. For example, we have a data set due to Hawkins in which the interesting feature is a hidden subgroup of outliers. We look at some surgical unit data in which there are two overlapping groups of data, and our methods provide ways of identifying the two groups and their properties. And then we look at some data from a bank. This is a larger data set, much larger, of course, than the kind of data sets that people were looking at for regression 20 years ago. There are 1,949 observations, 15 explanatory variables. The properties that come out in the analysis are the importance of the different explanatory variables and the presence of multiple outliers.
Question is whether the importance of a particular variable depends on the presence of particular observations. So what is the effect of certain observations on the importance and also on the sign of a particular exploratory variable?
So here is a very condensed version of the analysis of the bank data. What we call minimum deletion residuals are just the likelihood ratio test, or the square root of it, for the presence of outliers, and we monitor the properties of this as the subset size goes from being very small, here about a bit less than 500, up to the full almost 2,000 observations. We see that for a large part of the trajectories, the observed values lie nicely towards the center of these envelopes, and then at some point the outliers start to enter, and you get a large signal that there is that outliers are present.
Then maybe at the end you can have a masking effect.
That was using the forward search. Here is what happens when you use estimation. The blue residuals, you see, are all hang together and form quite a distinct group, and then the red residuals are extreme outliers. But they're extreme. There are more than these that were shown at the point where the trajectory on the previous slide suddenly shot up.
And it is also interesting to notice that at values of breakdown point close to 0.1, 0.15, then there is a sort of change in the ordering of the residuals. And this change is signaled by the monitoring of the estimates of the correlation coefficient between two consecutive values of breakdown point. Here, these plots on the right suggest that the model is stable, but for values of BDP a little bit larger than 0.1, there is a change in the ordering of the residuals. Beyond the presence of extreme outliers, there is another group of data which has a non-negligible weight when the breakdown point is below a certain level.
So what does this mean for the analysis of data? On the left-hand side, we have two values of t-statistics, and those for the 9th and the 13th variable. We can see that as the breakdown point decreases, the value of T9 goes from being positive to being non-significant to being negative, whereas that of T13 remains positive all the time, although varying quite largely in its significance. The forward search estimator, the plots are generally speaking similar. They're certainly very similar in a general shape. Again, T9 is significant for part in the middle, but not for very long. It finishes up very significantly negative. Whereas for T13, it's much more constant actually in value than it is for the left for the S estimation. But the general pattern is again much the same.
Also, another plot that we monitor is added variable T statistics.
This is probably rather difficult to absorb at a brief glance. The thing to notice is that all of these trajectories have a change at a particular value of the BDP, which was that was shown by the correlation plots that you saw earlier.
Right, and this value of BDP corresponds to a certain subset size. Beyond a certain subset size, there is a big change in the order of importance of the t-statistics, which implies a big change in the ordering of residuals. So here we are able to understand what is the subset size in which this effect starts to take place. Now we move to chapter 5.
Here we did some simulations to look at the practical comparisons of the different estimators. This is a size comparison. The nominal size in these simulations was supposed to be 1%.
Which is the red line, very, very close to zero, which is shown here. So all these estimators should have a size close to the nominal one, which is 0.01.
In fact, what you would find using these estimators is that you would find outliers everywhere. There are two different breakdown points for the S estimators, giving these two sets of 5 points. The estimators have a variety of efficiencies stipulated, and they don't seem to have very much effect in this case. And then the various forms of LTS have much too large sizes, but still less appreciably so than those of the M-derived estimators.
So the first comparison in terms of size, then the second comparison is in terms of power.
Here, this is what happens as the shift moves. The shift is how much some of the observations contaminated. But the proportion in this particular plot remains constant. You get similar but different plots if you had a higher or a lower proportion of contaminations. You can see that these are very, very nicely, really, like cumulative normal plots.
So all these curves tend to 1 when the part which is contaminated is very remote, but it is important to understand at which rate they converge to 1. Then we have another comparison.
So here what we have is two populations. We have a large blue group, which is the uncontaminated data, and then we have the red group, which are the contaminants. And we see what happens as the red group moves around. It goes up close, and then it goes through the blue group and out to the other side. And we can look here also at the power of the tests. When the two groups are close together, the power, of course, will be small. When the two groups are far apart, the power will be large, which will be larger or smaller for different estimators.
Now we move to chapter 6, and in chapter 6 we consider the transformation of the positive response.
This is using the Box-Cox transformation, power transformation. What we have here is a score statistic for that transformation, and you can see that for each of these trajectories is for a different value of the transformation parameter, and as the subsample size gets larger, 1 and -1, the extreme ones, rapidly are rejected, but the 0, the log transformation, stays inside these envelopes for the whole time, so that we can see that this particular transformation is not being affected by the presence of any outliers.
The additional benefit of this plot is that we can understand what is the proportion of observation which is in agreement with a particular transformation. For example, for the case of lambda is equal to 1, which corresponds to the hypothesis of no transformation, we can see that the value of the test starts going out of the band very early in the search. This means that the need of transforming the data is not due to the presence of a particular observation, but it is diffused throughout the data. Then we go on in order to show how you can automatize the choice of the transformation. We have an automatic procedure, and the results are summarized in a single plot with 3 panels. We have a BIC which enables us to understand in an automatic way what is the best value of the transformation parameter. Then we have another agreement index, and for each value of lambda we know the proportion of observations which have not been declared as outliers. Then the chapter concludes with the extension to cases where values of y can be negative. Chapter 7.
So far we have been dealing with parametric regression. Now we move to non-parametric regression, which, as our succeeding chapters show, provides a rich family of models for data analysis. The generalized additive model GAM for observation I has a general form that G of Y is a linear function of functions of the explanatory variables, that these functions are found by smoothing, and the G is found as a generalization one might think of as the Box-Cox transformation, but it's now found non-parametrically by numerical integrations of functions of the residuals. So you take some F's, you estimate them for a given G, you then, given the estimates of the F's, you estimate the G's, and you then iterate going backwards and forwards to convergence.
Here there is an example of the difference between traditional EVAs and robust EVAs.
EVAs was introduced by Riani, and it does all these things, but it's not robust. If you look at the lower panel of the right-hand panel, this is pretty much the sine curve that we simulated, and then we put in some outliers. So you can see that on the left-hand side, the non-robust analysis is deflected by these, distorted by these outliers.
So the outliers are denoted with the red circles.
Mm-hmm. So in the right-hand panel, they are omitted from the analysis. You can see, however, in the upper right-hand panel of the left-hand panel, you can see a plot of fitted values against the transformed Y, and there are clearly a strange pattern of residuals. This does not at all correspond to what we fed into the data. If you go to the right-hand set of panels for Ravers, we have a relatively smooth curve of transformed Y against Y, and we have a nice plot of fitted values, a bit of scatter around them, and then some very clearly articulated residuals. This is partly due to robustness, but there is, we think, a mistake in Tibshirani's estimation of the variance transformation from the residuals that leads in many cases to very strange patterns of fitted values and transformed Y, and we strongly recommend that even if you do not want to use robust methods, you should use our version rather than his.
Now we move to Chapter 8, and in Chapter 8 we consider extensions of the multiple regression model, a variety of extensions.
Yes, all of these in the book are illustrated with examples. We look at Bayesian analysis, that is, when there is some prior knowledge about the values of the parameters and of the error variance. We look at heteroscedasticity. We look at robust regression clustering. We look at the robust monitoring of time series. We look at regression with compositional data, and we look at censored regression. In all of these, the robust methods that we have developed provide interesting insights into the data.
For each of them, there will be a video. In Chapter 9, we move to variable selection.
There are two things that we've looked at here. One is extension of CP, value CP, to a robust form of it, and a visualization of the results during the forward search of this CP, which we call a generalized candlestick plot. And the other one is to look at regularization methods such as the lasso and sparse LTS regression, where the model that is fitted is not least squares, but has a penalty function included in it.
And here we see an example of where this penalty function is estimated each time for each value of the breakdown point.
This seems on the surface of it to be a chaotic plot. However, it has been plotted so that each blue dot indicates which variable is included in the subset that is found. Those that occur most frequently are plotted at the bottom. And it's interesting to note that there is a very nice very nice band there of variables that are included quite frequently. And we then proceed to a second analysis using this information from this robust analysis that has used sparse LTS.
Yes, on the other end, there are variables that are included just for particular values of the breakdown point. We conclude with the chapter 10.
This is really taking the methods that we have developed and applying them to the analysis of 4 data sets.
In this analysis of these data sets, we apply all the concepts that we have seen in the previous chapters. We apply the concepts of transforming the response, of analyzing using an heteroscedastic approach if we think that the variance of the residuals depends on a range of values of particular explanatory variables. At the end of each chapter, we have a set of theoretical and computational problems. The solutions of all of them are included at the end of our book. So we have fully worked solutions. Finally, about the software, the codes make extensive use of the FSTA toolbox. All the figures are reproducible either using the free version of MATLAB, which is the MATLAB Online, or in some cases R. For all the files, we have also provided the Jupyter Notebook version.
We hope you enjoy the book and your extended data analyses. And if you find anything at all wrong with the book, or anything you like, of course, do please let us know.
Yes, please let us know. Thank you very much.